Okay, so let's talk about 25.1 to 25.5, geometrical optics. So we're going to talk about the ray aspect of light, the law of reflection and the law of refraction, total internal reflection, and rainbows and prisms and dispersion. Okay, so you may have heard that we can treat light like a wave that has a wavelength and a frequency and an energy and this kind of things, and we talk about interference and superposition of waves and blah blah blah. Well, we can also treat light as though they are individual rays when we're dealing with macro objects, because the wavelengths of light are so small that for just the propagation of light, it's simple enough to use what we call let's see, where is it? The branch of physics called geometric optics. So we treat light as individual rays coming in, and we imagine them coming like that. And you could imagine that they're wavefronts arriving and other things like that. But it's very simple, and it works very well for macro level objects to treat them as just using simple geometry and imagining how straight line rays will behave. So the first example of ray optics is the law of reflection. And the law of reflection says that when a ray of light hits a mirror surface, it is reflected at the same angle that it comes in. So the incident ray is equal to the reflected ray, the angle there. So this angle of incidence, is equal to the angle of reflectance. Okay, so that's all it is. That's the law of reflection. It says that an incident ray reflects off at the same angle that it came in. So if it came at a glancing blow, it would leave at, so that angle would equal that angle. Okay, so that's just a fact that we've noticed. If the surface is rough, the reason our surface is not shiny, for example, is because the rays are always bouncing following this rule at every point, and it's different, so they don't add up like they would on a polished surface. Okay, so this would be an example of the sheet of paper. When you shine a flashlight on it, light is bounced away at all different angles because it's a diffuse surface, and the surface is rough, and the light gets scattered everywhere. For a mirror, you have a very smooth surface, and the rays of light being bounced right out, and they don't scatter as much. That's cool. It's the moon and moonlight scattered off a lake. Okay, so then the law of reflection, when it applies to a mirror, one of the questions that's generally asked physics students is, how much of a mirror do you need in order to see your whole body if you want to see, what your shoes look like, and so on. A lot of people go to Target and they buy a full-length mirror so that they can see everything. Well, you end up, if you get a full-length mirror, you end up seeing the carpet in front of your feet more than your feet. So in order to see your full body, because of this law of reflection, bing, bing, to get to your eyes from your feet, you only need a mirror that's half your length. So however tall you are, if you get a mirror that's half your height, you'll be able to see your full body in that mirror. So this is an example of the law of reflection, and the way you do the law of reflection is you need this perpendicular line to the surface. So there's your surface, there's your perpendicular line, and then the light ray that comes in and is reflected, those two angles equal each other. So your first step when you're doing problems like this is to draw your surface and then a line perpendicular to it that you can reference your incident and reflected angles from. Okay, and moving on. Okay, so then that's the law of reflection. The law of refraction says that when light enters a different medium than it's going in, so for example, when a light ray leaves air and enters water, or enters glass, or enters quartz or something like that, light will bend a little bit, and that process of light bending is called refraction. And we're not going to get into too much about why that happens. Suffice it to say, it's very complicated. But simply speaking, using geometrical optics, here's an example of one fish looking like it's in three spots because of the way the light is behaving. what it does basically, I guess there's a little bit of an aside here, but when light travels through a different medium, it gets refracted, it gets bent, and there's a law associated with it. But they talk quickly about how the speed of light is constant, and the speed of light is about 3 times 10 to the 8th meters per second, 3 times 10 to the 8th meters per second. Well, refraction happens because light slows down when it enters a medium, when it enters water. So let's say you're in air, light's going full speed, boom, hits water, and then it's going to slow down. Why? Because light is photons, and when photons enter something like water, the electrons in the water absorb the light and re-emit it, and then the next electrons absorb and re-emit, and the next electrons absorb and re-emit. So there's a time delay, a process there for the light to be absorbed and re-emitted and absorbed and re-emitted as it travels through the material. There's a little section here on the speed of light and how it was first measured by Michelson and Morley. Actually, it might have just been Michelson. Yeah, well, Michelson, I should say. So Albert Michelson and then Morley, those were the two guys who nailed down that the speed of light is constant and that it doesn't change with respect to any sort of motion of the Earth through the solar system. So it was constant for everyone, and that's what led to Einstein's postulates about relativity, and just said everybody agrees that the speed of light is constant, and we'll talk about that in a few chapters. Okay, so what happens when light enters a material? It slows down, and it slows down based on a property called the index of refraction of the material. So, for example, let's say the speed of light, c, is equal to n times v. Okay, that means v is going to be, okay, if c is constant, if the speed of light is constant, and we need to make sure n times v equals c. If velocity goes down when it enters a medium, that means n is going to be greater than 1, because then v is less than c. We have to increase it with n, something greater than 1, to get it to equal c. So that means the index of refraction is a number greater than 1, and here's some examples. So air, other gases, things like that, the index of refraction is very close to 1. Liquids like water, it's about 1.3. Benzene is 1.5. Diamond, this is why diamonds sparkle, because it has a very high index of refraction, so the light gets refracted very strongly, so it ends up sparkly. Ice, same as water almost. Quartz, 1.4, 1.5. Zircon, 1.9. Okay, so zircon very close to diamond, so you can get some interesting things there. Okay, so you can figure out the speed of light in zircon, for example, which is 1.9. So v equals c over n. So the velocity of the speed of light in zircon is going to be c over n. So you end up about half the speed of light in zircon. So it slows down. So this is fiber optic cables, light that's traveling around in fiber optics. It actually slows down, travels much slower. So when we do communications around the world, we joke that their speed of, they're communicating at the speed of light. Actually, it's much slower than the speed of light because the light that's doing the fiber optic, traveling through the fiber optics is already slow, plus the electronics processing all the information and then retransmitting it over the air and blah, blah, blah. So it's almost light speed, but it's still very fast. So the law of refraction is best summarized with this equation called Snell's law, which says that the incident angle is equal to the refracted angle, similar to the law of reflection. This is just a little bit more complicated because we got a sign on it and our ends on it, but it's pretty simple. These two pictures are stupid. This makes zero sense to me. I don't know what's going on with these lawnmowers or why they're using lawnmowers. And I mean, I kind of get it because they're trying to say that this tire, when it hits the grass, is going to be bent this way. Nah, some stupid thing. Okay, so let's show you what a normal person would have. Okay, so let's say, okay, let's say we got some water. What is this, a colored pencil? What's going on here? How do I change the color? Whatever. Let's say this is water. Let's Let's make it even bigger. Okay, so let's, oh my gosh. All right, so there we go. We've got some water. And first thing you do with these Snell law problems, again, with the law of reflection, same thing. You draw a line whoop, that is perpendicular or 90 degrees to the surface, because from there everything happens. Okay, and then your ray of light is going to come in being like that. And this angle from the line you drew straight up and down and your new line is the incident angle. Okay, the refracted angle, boop, is down here, theta refracted. Okay, so your incident angle and your refracted angle are always measured with respect to the normal line, or that line that's straight up. So let's go over to these stupid drawings. You see that angle 1 and angle 2, they're all measured with respect to this dotted line that's up and down. Okay, so that's your incident angle, and this is your refracted angle. And when you're going from air, for example, to water, that means you're going from n equals 1 to n equals 1.33, and that means you're going into a higher index material. So that means your incident ray, bink, is going to be bent towards the vertical line that you drew. Okay, it's going to be bent towards the normal, as we'd say. So this line is often called the normal, and normal usually means perpendicular to the surface. So this is the normal, and so we would say the incident angle is refracted towards the normal. Sorry, with the refracted ray is refracted towards the normal because it's brought closer to that line. So our refracted angle is going to be less than our incident angle. And the way this works is we say that the relationship n1 sine theta 1 is equal to n2 sine theta 2. This means that there's a relationship between these two. So n1 is 1, so we'd have 1 sine theta 1, and n2 is 1.33, so we'd have 1.33 sine theta 2. Okay? And then, or, theta incident, instead of, I could call this theta incident, theta refracted, so, and call this theta refracted. Okay, and so so this is how you do that problem. So now you've got an equation set up here, and let's say our incident angle is 60 degrees, or yeah, let's go with that. So then we'd have sine of 60 degrees is equal to 1.33 sine of theta r. We could take the inverse sine of both sides, and so we'd have well, we'd take sine of 60 degrees divided by 1.33. We'd take the inverse sine of that, and then that would equal theta refracted. Okay, and so that's how we could solve for our refracted angle to figure out, if we knew what our incident angle was, we could figure out what our refracted angle was. Okay, blah de blah de blah. Okay, so these types of problems, very straightforward. How you do them, a little bit tricky getting used to the signs, and you got to remember that if you have sine of theta, if you want to get theta by itself, you have to take the inverse sine of that, sine to the minus 1. So you'll have an operation like that on your calculator. That's how you undo a sine to get the angle that you want. And then also pay attention to whether your calculator is in degrees or radians, both fine units for angles, but you're probably going to want to be in degrees when you're doing this stuff. Okay, so let's think about this then. You've got your surface, you've got this surface, you've got an angle like this, and as we get the angle, well, okay, let me draw it the other way. So now let's say we're going from 1.33 to 1, so we're going from water to air, and we bring our ray in, boop, and as we get this angle closer and closer to the surface, boom, there's a point where the angle as the, can I change the color, please? There's an angle where the the refracted angle is 90 degrees, okay? So our incident angle is here, and if we make our incident angle large enough, there's a point where as we get closer and closer to what's called the critical angle, this is the critical angle because our refracted angle is 90 degrees. So you can imagine you've got n1 sine theta 1 is equal to n2 sine of 90 degrees. Okay, and that's the special case for the critical angle. Now this incident angle becomes the critical angle. And that's the case where you have total internal reflection. So if you're up here, this is your eyeball, and you're looking down towards the water, you will see rays coming out for angles less than the critical angle. But when you're at the critical angle, light never leaves the water. So at that point, no one above the water will be able to see what that ray is doing, where that's coming from. And that's called the critical angle. And the critical angle is equal to n2 over n1, right? And then the inverse sine of that. And that is what's going on. So you're going to have, when you go from a higher index to a lower index, so let's say you're in water and you're shooting light out into air, you're always going to have a refracted ray and a reflected ray. And then there's a point where you have your critical angle where the refracted ray is at 90 degrees, okay? And then above that angle, any place above that, you have what's called total internal reflection, and that is how fiber optic cable works. Fiber optics cables work. So there's your critical angle when you're going from some medium to another one. Okay, and so fiber optics, endoscopes, telephones, all those things, you basically have the light bouncing around because they're always trapped within the reflected and refracted angles. Well, the refracted light is always above the critical angle, so light just boom, 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 never escapes out into the surface. Okay, and that's how you get light into weird spots in your body. Okay, there are special reflectors on the surface of the moon where this is how we measure how far away the moon is. Light, there's special reflectors where no matter what angle comes in, or no matter what direction the light ray comes in, it gets reflected right back out. And boom, boom, just like that. Okay? And, yeah. Anyway, so then you've got binoculars here, you've got some optics in here showing you how the light bounces around in there. Diamonds, same thing. That's how diamonds, they're so shiny. Okay, so those are your main ideas. And then there's a process called dispersion. And dispersion is what it sounds like. It's the dispersion of light into different angles. So it actually turns out that the index of refraction, n, is slightly different for every color. So what that means is that our angle, usually we ignore in these equations, we ignore the wavelength of light, but in the true equations for geometrical optics and incident and refracted rays, you will have a dispersion relation there that tells you how the angle changes as a function of wavelength. It's a little complicated and not super necessary for most of what we do, but you can't understand how a prism works if you don't understand that, so it's a little bit tricky. But suffice it to say that this table here of indices of refraction, here there would be n for red, n for blue, n for green, n for infrared, and for X-ray. The index of refraction changes for all the different colors. What that means, if n is changing, then so are your refracted angles. Your incident angle will stay the same because it's the angle you're injecting light at, but since n2 and n1 are slightly different for the different colors, then your refracted angle is going to be slightly different. What that means is that you get problems with cameras having chromatic aberration and different things like that, where the pictures they take aren't in super great quality, because if you have a lens and you've got light coming in and then refracted, but the red light that's coming in is refracted at a different angle, then the lights don't combine. And same thing, green light's coming in and it's going something like that. What you would want them to do is the green light comes in, the red light comes in, boom, and they all meet together at some point. Then they'll be in focus, and then you'll see what's going on. But the fact that they don't is what allows us to use a prism to split light up into its colors and then make that into a spectrometer or something. So there's your visible light spectrum from red to blue or violet, and from 400 nanometers to 700 nanometers, in that range, about what your eye can see. And you can see that for the index of refraction for red, orange, yellow, green, blue, violet, 1.331, 1.332, 1.333, 1.335, 1.338, 1.342. So you can see they're very small changes to the index of refraction for these different materials. But it's pretty cool. Our incident light, boom, boom, when it gets refracted, that refracted ray, that angle is slightly different for all these different wavelengths, and so then you end up with this dispersion that's happening, and it gives you that really cool effect. So that's what's happening inside of a rainbow. Sunlight's coming in, the different colors of light are getting refracted at different angles, and as they bounce around and then eventually leave the rainbow, or the water droplet, boom, boom, then your light is separated into that rainbow. And so you'd have, yeah, we've got a diagram here. Basically, you've got your water droplets, and the sun's coming in, and they all come in at about the same angle, and so they all leave at about the same angle, and then you have, and it's like 42 degrees or something. And then you get this rainbow that actually is a full circle. Depending on where you're standing, you'd be able to see it. But that, you know, usually the sun's here, and so the ring is kind of around that way, so you aren't able to see the bottom of it. But that's why you need to be, the sun needs to be behind you, the clouds and the rain needs to be in front of you, and then you'll see the rainbow because of the way the light is reflecting out of the sun. So this would be a full circle all the way around. And this is pretty cool. There's actually, in this case, the double rainbow. And if you ever see a rainbow, usually you can see the second rainbow too. But you see there's ultraviolet here, and, well, not ultraviolet, but violet here. You got violet there. You've got red here. Notice you've got red here and violet there. And so the rainbow here is a mirror image of itself. That secondary rainbow is a mirror image. So pay attention to that the next time you see it. Okay, talk to you later. Bye.